it counting? Okay, so welcome everybody to the 5th lecture. I have to really apologize for the absolutely appalling video quality of what's on YouTube. We had a 60 Hertz loop and, well, we found out after the fact. So never assume your equipment works until you've tested it. That's why we have a slightly ridiculous setup of a microphone and a tripod here in front and this in the back. This time it should, fingers crossed, really work. Okay, so are there any questions about last week's lecture before we get started with this week? Any questions whatsoever? I mean, we had a fair amount of math, and so basically this lecture now, and maybe the one next Monday, are going to be probably some of the technically more challenging lectures of this class. So Leila, I think, yesterday went through some linear algebra and also a little bit of Banach spaces, norms, and so on. That'll be useful. My guess is we might have a little bit more about function analysis eventually. So unfortunately, machine learning does involve math, and yeah, okay, we're stuck with it, right? But math is beautiful, so at least I enjoy it, and I hope I'll convince you that it's fun. So let's get right started. Good. So remember we had this theorem called Mercer's theorem, right? And well, that one said in matrix speak essentially that a kernel is a proper kernel if the, vector matrix vector version, so that's the thing down here, is always greater or equal than 0. Of course, that means all the eigenvalues are greater or equal than 0. And the very same thing holds for, well, functions in this case. So except that, you don't have a finite dimensional sum anymore, you have an integral, and that's about the only thing that really changes. And then wherever you had eigenvectors, now you have eigenfunctions, but you still have a discrete number of eigenvalues here. That holds in slightly more general cases. And so once we had this, all we needed to do is we just took whatever we had in terms of our perceptron on features and did a query replace into a perceptron using kernels. That's about the only thing that changed. Right? Now, the nice thing is that you can therefore have a very modular system where on one end you code up your kernel algorithm, and on the other end you go and design the right kernel. And for about a decade this proved to be a very beneficial and efficient task where you could just go and write a lot of kernel papers where you design a new kernel, and then show that therefore 5 other algorithms would work better on the types of data sets of your choice. And likewise you could design new learning algorithms which would work on all those data sets because people had already designed kernels. So this is a very nice of making things modular. But what you need to do is you need to check whether the thing that you're dealing with is actually a kernel. And Mercer's theorem gives you the conditions for it. Now before we go and actually use this in a lot of other specific cases, let's look at some of the things that you can do if you have a kernel function. So the first thing is you can compute distances, right? Mind you, those distances are now between points in possibly an infinite dimensional space. So nobody said that these kernels actually map to any finite dimensional spaces. As a matter of fact, there are a whole bunch of proofs which show that they map to infinite dimensional spaces if you choose the right kernel. And this is also why you really want to use a kernel as opposed to explicitly map to those spaces, at least in a lot of computational settings. Okay, so let's take the squared distance. Okay, that's phi of x minus phi of x prime squared. Okay, we can expand this, and actually let me do a slightly more detailed derivation on the nodes. Wrong. Display needs to be the right one. So remember we want to get the squared distance, d squared, between x and x prime. Well, that is the norm squared of phi of x minus phi of x prime. That is, well, the inner product of this term with itself, right? I guess you don't need me to write that out explicitly, but you can see that this is the same thing as phi of x dot phi of x plus phi of x prime dot phi of x prime plus 2 phi of x dot phi of x prime. Minus. Thank you. Thank you, this is good. Okay, now, all we have to do is just in each of those cases explicitly, plug in what the value of the kernel is. Now we know what the values of the kernel for this, that, and that quantity are. After all, that's on the slide over there. And so we have a means for computing distances. So it's very easy. So what this means is that you can now compute distances in infinite dimensional spaces, even though you never really went into that infinite dimensional space. Yep.
On the last line, should that be negative 2k xx prime?
Correct. And if it isn't there, then I made a typo. Thank you. I need to fix this. Thanks. So let's take some kernel that we're going to see many times over, and that's the RBF kernel. And we'll look at that in some more detail today and also then next week. K of x and x prime is x of minus some coefficient lambda, maybe lambda over 2, norm of x minus x prime squared. So one important thing, this kernel here is different or not necessarily the same as the kernels that we looked into for Parson windows. The kernels for Parson windows sometimes can also be suitable kernels for this here, but they need not. They are also obviously not operating systems kernels. I'm mentioning this because many years ago I got emails from very eager students who wanted to do their PhD with me because they had done work on kernels. And their pedigree was Linux kernels, and I forwarded them on to the systems guys, so who were very happy with the students, but yeah. So just because two things are called the same thing in math, they don't have to be the same. So just be careful that Parson Windows kernels and, well, as in, Hilbert-Schmidt kernels are not necessarily the same thing. In some cases, we'll get similar expansions and we'll be actually able to compare the solutions in both cases, and we'll see how they differ slightly. But this is just a caveat. Now, if I have this kernel here, then it's very easy to compute k of x and x, right? Because, well, what's that? Can somebody tell me the value of k of x and x? 1. Exactly. Perfect. So what does that actually mean for the data when it's mapped to this high-dimensional space? Can you give me a nice characterization of the space in which this data lies in? If the length of each of the points in feature space is 1, what kind of object is that, where all points on that object are 1 away from the origin?
Sort of hypersphere or something?
Exactly. It's a ball, right? It's basically, it's basically the surface of the unit ball in that Hilbert space. Actually, it gets even cooler. Because, remember, this quantity here obviously is greater or equal than 0, because we have the exponential here. So that means that the angle between any 2 points is never larger than 90 degrees. So what's really happening is we have the space in super high dimensionals, but any 2 points will not be further apart than 90 degrees. We're just mapping points onto that. It's kind of a really nice construction. And you can actually do interesting geometrical reasonings, like, for instance, the smallest enclosing sphere would be equivalent to a hyperplane that's pushed out as far as I can and separates the data from the origin. And we'll actually use that intuition later on. But it also means that this distance here now becomes something very simple for the RBF kernel. This just becomes nothing else than 2 times 1 minus e to the minus lambda over 2 x minus x prime squared. So now you can see that the distance is at most 2, well, which jives with the fact that they're all in a unit sphere and the angles are never larger than 90 degrees. Because, as you have really higher and higher dimensions, I mean, orthogonal vectors are, as far away as you can want them. And then, well, this is basically just a similarity measure, right? So this is a similarity measure that you might have dreamed up otherwise anyway. Now, I cannot go and just plug in any function in here, but there's actually a large class of functions which will work for this. And because this class of functions is so important, they are called translation invariant kernels, and they have the property that k of x and x prime is given by some function kappa of x minus x prime. And quite often that function will actually only depend on the distance between those two. Okay. So, any questions about that so far? Yep.
How do you define the inner product in
Okay, so how do I define that inner product? So first of all, for the purpose of doing any math with it, I don't have to, right? Because all I need to do is I just need to prove that that function k satisfies Mercer's theorem. So I only have to prove that it satisfies the theorem. I don't have to give a constructive proof. It's a big difference. The other thing is that, as you all know, well, rotations keep inner products the same. So in other words, if I have two vectors here, and I rotate both of them, let me get these vectors, then now the feature map, of course, is going to look different. The explicit feature map for these two guys is going to look different than from those. Let's say here is phi of x prime, and here I have some, let's say, psi of x and psi of x prime. If I only know the inner product, I have no way of distinguishing between phi and psi. Because for all pairs x and x prime, what I'll get is that phi of x dot phi of x prime is identically equal to psi of x and psi of x prime. So this is good and bad. It's bad because, well, there is no one right unique feature space representation. It's good because for some computations you may actually want to pick a specific representation that you like. And this might actually let you do certain computations really very rapidly. So that's why this is actually a blessing in disguise. Thanks, that was a good question. Any more questions? Yep.
Can you explain why the angle between 2 points cannot exceed 90 degrees?
Okay, so this is the case only for this specific RBF kernel. It does not have to hold in general. So for instance, if I have a polynomial kernel of odd order, I can very well get something that's larger than 90 degrees. But you know that if the inner product between two vectors A and B is greater or equal than 0, the angle must be less equal than 90 degrees. That's basic geometry, right? And if you look at this function here, you see that it's greater or equal than 0 for all x and x prime. So therefore, you must always have angles less equal than 90 degrees. Right? Okay. I guess the phone agrees. So, let's move on to something else here. The next thing is to, check what that matrix looks like. So my claim is that this matrix K is positive semi-definite. Positive semi-definite means it has all eigenvalues greater or equal than 0, and it's also symmetric. Now symmetry is trivial, right? Because we have our kernel being symmetric. To check for positive semi-definiteness, well, we need to check that this expression here for all possible alphas is greater or equal than 0. Well, all I do is now I push the sums inside that inner product. This is a bilinear form in the first and the second argument, so I'm allowed to do that. So I push the I summation into the first part, the J summation into the second part. There we go. And now we're done. Because I now have on the left and right hand side the same expression there. So this is the norm squared. This is all stuff that we knew from basic linear algebra, except that we now have those pesky phi's sitting around. But other than that, this is exactly what you already knew from a long time ago. And so therefore, you can see that for any kernel matrix, this will always hold. As a matter of fact, that's a really useful way of checking whether your kernel is a kernel. So a colleague of mine, fairly well known, well respected and whatever, I met him a couple of years ago at a conference. And he told me about his new kernel, and it worked really well in practice. And he was trying to prove that it actually was a proper kernel. He couldn't prove Mercer's theorem. And he'd spent significant time on it. And well, so he showed me his proof, and so I asked, did you ever check it? And he looked at me, got a little bit quiet, and then, 3 or 4 lines of MATLAB later, I said, by the way, here's a counterexample. He was not happy that day, but what I'm trying to tell you with this is, in many cases, if you have a very nice theoretical idea, just run a very quick test, at least a quick sanity test to check whether your theoretical idea is okay. Otherwise, you might end up wasting a lot of time. Yeah. Anyway, the other thing is we have this kernel expansion, right? So W of phi of Ax. If W is given by this linear expansion, sum over alpha I, phi of xi, then I can do the reverse trick of what I did above, namely I pull the alphas and the sum out. And so I get that inner product between phi of xi and phi of x, which we know is k, and so we now have this kernel expansion. So for maybe about 5-6 years, and I'm very sure there are still algorithms out there where you can do this, maybe not directly in machine learning anymore, but other areas. It was a very profitable franchise to take an existing algorithm which was written in terms of inner products, or just some nice linear algorithm, linear as in working on inner products, and to kernelize it. And so you would basically have to go back to your favorite books from the 60s where they did this, where they worked on linear methods. Very beautiful theory that was then forgotten because of course it was only linear. And then just to replace inner products by kernels to make sure that you don't overfit, and you will get fairly new and significant and great algorithms out of it. So for instance, if you do economics, so recently somebody worked, so Sebastian Lahaye and co-workers, they worked on a nice pricing curve where before that people used linear methods and they kernelized it, and it's an awesome paper. So it's not just in machine learning where you can use it. I bet you if you don't do machine learning and you have some nice linear tools, think about how you could kernelize them, because that might very well be a blockbuster paper. So far, most of those kernelization papers have been very highly cited. So if you don't do machine learning, look at what you're doing. You might have a nice paper, nice result sitting on your desk. Okay, any questions so far? I know I'm going through this extremely slowly, but I just want to make sure that everybody is really on board with this, because this is mathematically probably the most challenging part. So here's an example for something that isn't a kernel. So a nice similarity measure would be k of x and x prime. It's 1 if x and x prime are close, and it's 0 otherwise, right? Symmetric. You can actually use that. And one of those kernels that actually have persisted for about 10 years was the hyperbolic tangent kernel. So you'd basically take an inner product and then take the hyperbolic tangent of that, also called the sigmoid kernel, and people wrote papers about it and how great it works, and nobody knew whether it was a kernel until at some point we proved that it cannot be one. That stopped people from actually using this kernel to some extent at least. But in this case, it's actually very simple. I mean, for this simple function, well, you just construct a kernel matrix. It's not really a kernel matrix. You then run that through your favorite linear algebra system, and you get those eigenvalues. And you see that you're screwed. So it's not a kernel. So proving that something is not a kernel is sometimes a lot easier by just counterexample. And you might get some understanding on the way. Okay. Here's some examples of stuff that is a kernel. First one we've already seen. This is just the inner product, right? Another one that is also a kernel is just, the norm. Then this one we already encountered. The polynomial kernel, that one we already encountered. Then B-splines are also kernels. And, well, the conditional expectation. So in other words, the joint probability between x and x prime, if they're conditionally independent of each other, is also a kernel. Now that sounds like, why would anybody do something as crazy as that, right? This actually has a very nice application in biology. Let's say I have two biological sequences and I want to find out how similar they are. So then what I can do is I can have some, models of, how sequences evolve. In other words, I can have a model of, p of x given some sequence c. So that's an ancestor. And so I could say, well, two sequences are similar if they're likely to have had a common ancestor, and they're dissimilar if they are not so likely to have had a common ancestor. So C is the common ancestor, and you might have some distribution over those guys, and then you need to solve this integral. And it turns out that for certain hidden Markov models, so pair emission hidden Markov models have exactly that property where if you take the expectation, you can actually, through clever dynamic programming, work that out. And so David Hausler and Chris Watkins more or less independently came up with this idea. And that was David Hausler's probably last machine learning contribution before he switched completely to bioinformatics. So he was probably one of the people who made sure that the Human Genome Project, the academic version, actually had a chance. Yep?
Are there any constraints on the probability when you choose for the conditional expectation?
No, there are none.
Just any?
You could pick any, except that in many cases it might not be a very good kernel. So that's another thing. So just because I have a kernel doesn't mean that it's actually going to work particularly well. And we're going to understand a little bit better what makes kernels good or not good next week. So when we'll go and have a look at regularization theory. This is going to be a reasonably mathematical part, and we will not ask that in the exam, so don't worry. So if that'll be a bit tough going. I mean, don't worry, but I want you to at least get some intuition for why some kernels are good and some kernels don't work. Because otherwise you'll be just using that tool without any understanding. Yep.
So how did you check that the previous kernel wasn't a kernel and
Okay, so how did I check that this kernel isn't a kernel? Well, I picked 3 points. I picked the points 1, 2, and 3. Then I go and compute the kernel matrix. That's the kernel matrix. Like this. 1 is, only 1 distance from 2, and 2 is only 2 distance from 3, and so on. But 1 is, of course, 2 distance from 3, and likewise. So I get this matrix. And then I type Python, import numpy, then you set m equals this beast. You may have to also import SciPy. You run the eigensolver of SciPy, which takes microseconds because it's a 3x3 matrix. And you plot the eigenvalues. Or you do that in MATLAB or Octave or Mathematica. Or you can just squint at it and see the solution, right? So that's all you need. That's game over. Yep.
So we know that if k is a kernel, then the kernel matrix should be positive and negative. But say if we have a candidate kernel, we don't know it's a kernel or not. We choose our points and we find the matrix is positive and negative. But we choose this point.
Right.
Does this mean this is a kernel?
Okay, so it is a necessary and sufficient. It's a necessary condition that the eigenvalues are greater or equal than 0. It's a necessary condition. So therefore, if you find such an example and it's not satisfied, you know the kernel's dead. If you know that it's satisfied, doesn't mean that, because it's a necessary and not a sufficient condition, it's only necessary. Right. Now, what you can do, because computing time is cheap and your brain time is expensive, you just generate a lot of random matrices and you check it out, right? So, your computer can test for probably 1 million matrices, and only once, they all come back okay, everything's fine, right? So one thing to be careful though, if you actually do this, right? You will occasionally find that the eigenvalue is a little bit negative. And that's just numerical instability. So if your eigenvalues are like -10 to the -10, there's a good chance that your eigensolver simply screwed up. So don't throw your kernel away because of that. Because that's also something that you can prove, for instance, for the RBF kernel, that the eigenvalues decay fairly rapidly. So even though this is maybe a 1,000,000 by 1,000,000 matrix, most of the eigenvalues will not matter. Mind you, for a 1,000,000 by 1,000,000 matrix, you will not do that anyway. You'll have to use something much smarter. So the B-spline is also a kernel. So B-spline is basically the convolution of the indicator function with itself. And something very curious happens here. So here's what happens. Basically, you take that unit interval and you convolve it with itself. And so you get from that this. You then convolve it again with the unit interval. And you get this guy. Remember this guy, this was the Epineshikov kernel. Somebody asked, wouldn't that be a better kernel? Can we just chop the parabola? And then you keep on going and you get something that's, order 0, 1, 2, 3, 4. So you basically get, piecewise continuous function. Actually, sorry, I cheated. It's not quite true because this would be continuously differentiable. So that's actually what you get. Now, an interesting thing that happens is that the support of this object grows linearly as I keep on doing this. Does somebody have any idea what the limit of this operation here is? I mean, yeah, we have to keep on squeezing it together, otherwise, it'll just run all away. But what's the limit of this procedure? It's a Gaussian. Yes. Why is it a Gaussian? Any suggestions? By the way, the answer is correct. Because convolving things, like this, which is essentially equivalent to a uniform distribution on the unit interval, you'll just get, as the limit of a sum over a lot of random variables, you get a Gaussian. So I learned that trick from Grace Wawa. Because once you think about it, it's completely clear that this, infinite convolution will give you a Gaussian. And it's such a beautiful trick. Now, an interesting thing that happens though is that not each and every one of those functions actually is a proper kernel. More to the point, this one isn't, this one isn't, this one isn't, and basically all the even numbers aren't and the odd numbers are. Which is very intriguing, right? Because they get smoother and smoother and smoother, and one of them is, the other one isn't. And so when we look at spectral properties of kernels, we'll see what's going on. The advanced answer already for what is happening there is, so this is one of those kernels that depends on the distance between points, and all you do is you just take the Fourier transform of that object, and you check whether that Fourier transform is non-negative. If it's non-negative, you have a kernel. If there are some negative parts in it, you don't have a kernel. So for some types of kernels, checking whether it's a kernel is really easy. Just Fourier transform it. And so what you would see is that for the unit interval, you get this sinc function, right? So you basically get this beast here. Right? And this screws everything up. So once I square it, things are okay. Once I multiply it with itself again, well, it gets worse. And so you see why one of them is the kernel and the other one isn't. The theory behind that is something we'll do next week. Another thing is for a dot product kernel, so one that has this form k of x in x prime, is some function kappa of x dot x prime. All I need to do is I need to look at the Taylor series expansion of kappa. If this has all non-negative coefficients, it'll be a kernel regardless of the dimensionality of the underlying space. For finite dimensional spaces, the analysis is a lot messier because rather than a Taylor series expansion, you're actually going to use Legendre polynomials. And this is not fun. But, you'd be crazy to do that. So you had a question before.
Yeah, you said why is Gaussian? Is it because Gaussian convolutes with the square method? You still get Gaussian, so that's a steady state?
Well, basically, yeah, law of large numbers. So, you get conversion to Gaussian, so everything is good. Sorry, any other question? Yep.
So is it possible that you get a candidate of kernel and that is actually not a kernel, but it works well for classical data set?
That can happen. And people have written papers about this. And they didn't realize that they didn't have a kernel and said, hey, gee whiz, it works. So now two things can happen. The first thing is simply, so actually three things can happen. First of all, they might have just gotten lucky. Right? So the second thing is there may actually be a subspace which, if you restrict the kernel to that subspace, is a proper kernel. The third thing that is actually also very common is that their optimizer simply is broken. So they didn't really solve the full, whatever kernel inference problem in the first place, and so that's why things didn't blow up. But if they had used, a optimizer that actually would have solved the problem, they would have probably run into trouble eventually. So that's actually the most common situation, that they used a kernel that was broken, they used an optimizer that was broken, and the combination of that, of two wrongs, sort of made it right. Don't do that. Okay. So here's some pictures of kernels. Right. You've probably seen a Gaussian before. Here's a polynomial kernel of order 3. It's a B-spline, so it's B3. So that brings us to the end of lecture 4. Namely, I think what, at least I hope I conveyed to you a little bit is, well, we looked at the perceptron, some learning rules there, features pre-processing, and now a fairly extensive introduction to kernels. Now we're going to go and use this kernel trick for some more problems, namely support vector machines. So if you have not done convex optimization before, now is a good time to know it. Yeah, and there'll be a recitation. Okay, so here's what we'll be doing. So classification, look at the optimization problem, support vectors, kernel expansion, and then, the soft margin problem. And I'll be treating those two separately just to make sure that everybody's okay with it. Otherwise, I wouldn't be going through it so slowly. So this is a nice explanation of how support vector machines work. Large margin of separation. And yeah, this guy probably made more cartoons. So I've sort of kind of given already the answer to the following conundrum away. So let's say we have ham and spam, right? And I can separate it this way. I could separate it this way. I could separate it that way. Or I could pick this curve, this line. So which one would you rather have? Okay, who votes for red? Okay, who votes for purple? Or whatever that color may be. Nobody? Who votes for black? Who votes for yellow? Okay. Test almost passed, right? So here's why. See, basically, the black line is the separator that separates the reds and the greens with the largest margin in between. Right. So now the question is, can we find that cheaply? The other question would be, after all, we have a perfectly good algorithm, right? The perceptron. Why on earth would you bother with this? And there are some good theoretical reasons for it. And for those, we might briefly touch upon them later in this course. But for a detailed analysis of that, this is really something that Larry and Artie would be covering in their class. Okay, so let's actually look at how we can at least get a solution. So, the linear function is f of x, it's w.x plus b. So we're starting again just with the linear problem, and we'll kernelize it later. So this is going to get us to state-of-the-art 1961 Vapnik and Lerner. Or no, sorry, 1963. Mangasarian had a similar paper in 1961 where he used a different definition of a norm. Other than that, very similar paper. And he used features already. Anyway, so what you can immediately see is that for all the green guys, w.x plus b has to be less equal than minus 1. And for all the red guys, it has to be greater or equal than 1. Right? So why did I pick 1? I could have picked 42. Wouldn't have made a difference. But I had to pick some number. And I picked the same number on the left and on the right because I want that separator to be in the middle of it. If you want to have something that's imbalanced, you could pick 2 here and 1 there. And I think there's at least one paper about that. Yeah, these were the early days. Now let's actually go and derive this. So, okay, here's the normal vector w, right? It's perpendicular to that hyperplane. The hyperplane in 2 dimensions, of course, is just a line, but more generally, that's some plane like so, and you have that normal vector sticking out, and with more than 3 dimensions Yeah, sorry, I can't tell. But you know what you immediately see is that there have to be points on that margin. So this thing here, this dotted thing, is called the margin. Well, why do I have to be able to find points on the margin? Well, very simply, because if there weren't any, I could just expand that further. So you could think of this like one slab and springs on either side, and you just slot it in between, and then the springs expand until it's nicely balanced. That's how you could view it. Anyway, so you have this, and well, of course, it means that there has to be some yellow dot for which w.x plus b is -1, and there has to be some yellow dot for which w.x plus b is 1. Let's use a bit of geometry. Okay, so we have those hyperplanes. Normal vector. Here's a point, here's another point. And so I'm interested in that distance here. So basically you want to find a linear separation for which has a large margin, let's call it rho. Now this margin I can compute by taking the inner product, by basically projecting this distance between, let's say, x1 and x2 onto that normal w. But not quite onto w, but actually onto the unit vector, right? Because that's what I'm after, right? I'm after this. So I would then therefore have to take x2 minus x1, and I take the inner product between that and w divided by its length. Right? And actually 1/2 for good measure. Now I can write this out as, well, 1/2 x2 dot w plus b minus x1 dot w plus b, which they cancel out, right? The b's go away. And then I exploit that, lo and behold, this quantity here is 1. And this quantity here is -1. And so I get that this is 1/2 norm of w. And that's exactly what we have here. Right? That's what we have. And yeah, I screwed up with the 2. Okay, good. Eisen, the slide is correct, and writing is not. So, well, that's actually quite nice, right? Because now we have an optimization problem. We have something that we can deal with. So we have the condition that w.x plus b is less equal than -1 for all the spam, and greater equal than 1 for all the ham. And at the same time, we want to actually maximize the margin. Right? We want to maximize the margin under this separation condition. Now, what I've done here is I've rewritten the separation condition in a slightly strange way. But it's just because I don't like if then else, and if I can replace an if then else with an equation, I'll happily do so. Okay, so let's just check that this actually is true. So pick yi equals 1, so all the ham. Well, then what I immediately get is that I just get x dot w plus b is greater or equal than 1. Okay, we're fine. If yi equals -1, I get that minus this quantity here is greater or equal than 1. So multiplying everything with -1, right? Well, what I get is that now I have this quantity here less equal than -1. You see, inequality also flips if I multiply with -1. Right? And that's all that there is to it. And then the other thing is it's kind of inconvenient to maximize 1 over the norm of something, so you might as well minimize the norm squared of the quantity. Just computation a little bit easier, and there are solvers for this and no solvers for the other problem, so that's how you would solve it. Okay. So this is something you really need to remember. So large margin separation, and it's a simple optimization problem. Now, of course, that simple problem doesn't really help you very much yet because you still need to solve it. So now let's solve it. Any questions so far, though? Everything clear? Everybody cool with it? Okay, good. Let's move on. So let's look at the primal optimization problem. I've just rewritten it. So the standard modus operandi for solving an optimization problem that looks kind of nice but not nice enough is, well, you might as well try the dual problem. Maybe the dual problem is nicer. In our specific case, that's actually a useful strategy because those W's may at some point end up, being objects in an infinite dimensional space. And for an object that's in an infinite dimensional space, that's really not so nice to manipulate. So you want to bring it down to a situation where you have a finite dimensional parameterization. More generally, when you have an optimization problem, what happens is that typically each of your constraints will become a variable, and all the variables that you had before will become constraints, and equalities will remain equalities, inequalities will lead to inequalities. Just the other way around. Free variables lead to equalities lead to free variables lead to equalities, and inequalities lead to inequalities. I apologize. So it's basically exactly the swapped. And we'll see a little bit what happens here. Remember, we have an inequality here. We'll actually get another inequality later on. And the strategy is you first start by building a Lagrange function. Now the Lagrange function, actually Lagrange, is by, well, you just take the objective function. And then, you have all those inequalities. You multiply, you bring everything to one side and you multiply it with a Lagrange multiplier. And you want to set it up in such a way that you minimize the primal variables, so the ones that you started with. And at the same time, you're trying to maximize this thing in those Lagrange multipliers. These will afterwards be the dual variables. And whenever all the constraints are satisfied, then the best thing that you can do is to set those dual variables to 0 whenever they would be violated. These essentially push against you. Who has done theoretical mechanics? Who's a physicist? Okay. So you've probably at some point had to read Goldstein, right? And you had all those virtual forces and constraint movements on a path and all that. Those alpha i's are your virtual forces. So you can think of them as forces that will keep the solution on the constraint set. Okay, so the physicists had a lot of this before us, but I'm not sure it necessarily is often explained in a more illuminating way in physics. So I hope I'll do at least not worse at explaining it. So, and there'll be a recitation on it. So, and basically what you can prove, it's actually a reasonably straightforward proof, but we don't have a lot of time for that, is that the optimal solution with regard to W is at a saddle point of that Lagrange function. So saddle point where if I fix the dual variables, it's the minimum in the primals, and if I fix the primals, it's a maximum in the duals. The only other constraint that you have is that these alpha i's here are greater or equal than 0. That comes from the fact that I have an inequality here. Had I had an equality here, I would have gotten free variables there. That's just as an aside. So, the way how you solve it is you take the derivatives in W and B, you get answers for W and B out of that, you plug that back in, and you eliminate W and B, and then you get a problem in the alphas. So here's what happens. So here's the Lagrange function again. I take the derivative in W. Well, the first term's easy, right? So 1/2 W squared, the derivative of that is W, minus, and then here we have a little product, so I can just pull that out, and I get minus sum over alpha I, yi, xi. And this has to vanish, so, well, what do we get? We obtain that W equals sum over I, alpha I, yi, xi. That's a really useful condition. The second thing that we get, if we take the derivative with respect to B, is that the sum over the alpha I and yi has to be 0. Remember that spring example that I told you before, where you squeeze that, slab with the two springs, so the two slabs with the springs connecting it in the. So the force from the left and the right hand side has to be the same. That's actually what this amounts to. So there's a physical analogy, as much as you can do physics in infinite dimensional spaces, between SVMs and this here. Okay. So now we need to plug this and sum over I, alpha I, yi equals 0 back into the Lagrange function. And, well, let's just do that, right? So we have L equals 1/2 norm of W squared, so we basically have sum over I and j, alpha I, alpha j, yi, yj, xi dot xj. Okay. Then we get minus, and here we have the sum over the i's already, so I'm just going to tackle that first term. I'm just going to tackle this part here. Well, what do we have? We have sum over the i's, alpha I, yi, xi transposed w. Now for w, we plug this term back in here again, right? So we get xj, yj, alpha j. Oops. And there's a sum over j, of course. And lo and behold, those two look the same. As a matter of fact, they are identical, except that this is 1/2 and this is 1. But let's carry on for a moment. So then, well, what else are we left? We have the sum over alpha I, yi times b. Well, that one is easy, right? We know that this vanishes here. And so all we are left with is plus, so actually let me just write it out. So we have minus b times sum over alpha I, yi. And then we have plus sum over I, alpha I. And this clearly goes out of the window. Well, this term here disappears, and this becomes a minus. And yeah, we get exactly what's on the slide. The only other thing that we still have is, of course, this condition here, because that's not automatically enforced. And we also have the condition that the alpha i's are greater or equal than 0. That's what we started with. And then if you want to ever read off the solution of the original problem again, you just plug in to this one here. So here's our problem. And that's how it sat there for about 3 decades. And then Isabelle Guyon and Bernard Boser came along. They were working at AT&T, and Wapnick was there as well. And they sort of toyed with the idea of, can we maybe use kernels? And yeah, basically in the end they got bored and actually did it, and they were quite surprised that it worked. I think they first actually had an argument about whether it was going to work or not. In any case, here's the optimization problem. Support vector hard margin. You can plug that into your solver and everything's good. Now a couple of useful properties. The first thing is, well, we have this kernel expansion, right? This kernel expansion says that W is given by the sum over yi alpha I xi. Now that looks very similar to what we had before for the perceptron, right? For the perceptron, we actually had W is given by the sum over yi xi for all the errors that we made, all the mistakes. So the key difference is that now we actually have a weight. That could be anything between 0 and infinity. Well, not quite infinity, but a very large number at least. Whereas for the perceptron, each observation got weighted with 0, 1. Any questions so far? Because the Karaj-Kontaka conditions are going to be a little bit technical again. Any question? Yep.
So when you transform the prime question to the dual form, so why is the minimum become maximum?
Because we have a set. So the question is, I went to the dual problem, now I have a maximization problem. Why? Well, you had a saddle point problem in L. So you're minimizing the primal, maximizing the dual. You get rid of the primal by essentially figuring out what the value of the primal once has to be for any value of the dual. But you still have the maximization problem, the dual. What you conveniently do is, if you squint at that problem here, you actually go and flip the signs here, right? You just make it a minus and you make it a plus, and then it's a minimization problem again. That's what people conveniently do, but I just left it as it was originally, because a convex minimization problem and a concave maximization problem are the same thing. But that's why you have a maximization here. Okay. Thanks for the question. Any other questions? Yep.
So instead of setting this problem as a constraint optimization, can you just use some unconstrained optimization techniques, such as you just derive the hinge loss and then go from there?
You know way too much. So the hinge loss is coming next, and I want to get to the hinge loss eventually. I just wanted us to understand so not this week, it'll happen next week, quite definitely. But yes, solving this hard margin optimization problem is of course not a good idea if you happen to have errors in your problem. But even for the hinge loss, you will get a mathematical program, so actually optimization does not necessarily always become easier. There are some cases when it does, but it doesn't necessarily become easier. Yep.
How do you choose alpha?
So alpha is what we get through solving the optimization problem, right? So
it's an output of the problem, it's not an input to the problem.
it's an output of the algorithm that you then invoke on the problem, yes.
Okay.
So it's an output as much as W is an output, right?
Right.
So it's like find X. The value of X is the output, right? It's that kind of thing. Now, there was another question here.
So why do you want to solve in a mode? Is it possible to solve in a Primal?
Very good question. So in infinite dimensional spaces, solving it in the primal is super awkward. You don't do that. So there are many cases where solving it in the primal is computationally or even mathematically impossible. That said, over the past 6-7 years, quite often people have found that there are approximate solutions in the primal that are computationally very attractive. Actually, I'll be talking about such a solution in 2 weeks in San Diego. So there are, in some cases, very good approximations to those inner products and to those explicit feature maps. And especially if you have ridiculous amounts of data, you may actually benefit from solving the problem in the primal. That has to do with the fact that those kernel expansions actually cost you computation. So if you have a lot of data, you get a lot of kernels. So that can be slow. But for you know, anything up to, you know, 5,000-6,000 instances, solving it in the dual is just fine. So, I mean, your laptop can do that. But basically, at some point, you know, you end up working with really big matrices, and I think about 10,000 by 10,000 matrices is where your computer will start being unhappy. Because now you're approaching a gigabyte of storage if you're storing them as doubles. And at some point, you have to invert those matrices. So 10,000 is about what your laptop can do. Above 10,000, it gets really tricky. Okay, now, Karas-Kontaka conditions. So remember what we had was we added into the Lagrange function this inequality times, you know, dual variable. And you can show that at optimality, this product has to vanish. Okay. Now, the fact that this has to vanish can only mean two different things. Well, either this term here on the right-hand side is 0, or the left-hand term is 0. I mean, they could both be 0, but at least one of them has to. So if this term here is 0, then the left-hand side can do pretty much anything it wants, but we know it has to be feasible. So we know that therefore w.x plus b, you know, all that times yi has to be greater or equal than 1. So in other words, if the alpha i's are 0, we know this point has to be somewhere over here. It could be touching exactly the margin, but that's about all we know. So for instance, if we see a point here, we know that this term here is, you know, non-zero, so this term automatically has to be 0. Again, necessary and sufficient. So if you see one of those red dots, you know the alphas have to be 0. If you're here on the boundary, well, you don't know. However, what you do know is that if the alpha i's are non-zero, then this term here has to vanish. Right? So in other words, these must be then points exactly on the margin. So what that really means is that in your expansion, you're going to expand only in terms of points exactly on the boundary. So I could give you the same optimization problem with all the red dots removed, and you will get the same solution. Which is a really cool thing, because it means if your solution consists of only very, very, very small number of points, maybe that actually corresponds to a reasonably simple solution. It also suggests that maybe you will only have a small number of mistakes. And there are actually learning theoretical bounds which count the number of support vectors and try to make inference on the solution quality based on that. But this reasoning that only alphas that only whenever the alphas are greater than 0, you know, you basically get something on the the other way around. Only points on the boundary can lead to alphas greater or equal to 0. So that reasoning is actually quite crucial for analysis. Okay. Any questions about that? Because this was a subtle point. Everybody clear or everybody lost? Maybe I should not take a vote on this now. Let's look at a few examples. All right. So, well, what we got is that, you know, this weight vector W is a weighted linear combination. Only the points on the margin really matter. You can ignore the rest. Only the inner products really matter. And we have a quadratic program. So we can actually go and replace this by a kernel. And the other thing is, well, we basically keep the instances away from actually the boundary, not the margin. Another typo here. So let's look at an example. Here's some data. And, well, lo and behold, you can see, you know, you get 2 support vectors on one side and 1 on the other side. Give total maybe of 15 points, and here's the separation. Isn't that nice? So why do you care about large margin? And, well, basically, large margins, you know, maximize, you know, the robustness against uncertainty. So you could, for instance, just say, well, I know each observation only with some epsilon uncertainty. You know, can I find a linear separator that still separates it? And so what I go is, and I just, you know, fatten up those points. That's the counterpart of, you know, the two slabs with a spring in between. I take a single slab and I just take each of those points and inflate them until this slab cannot move anymore. And that will also give me that solution. The other nice thing is that, you know, it's a reasonably nice optimization problem. Okay. Any questions about that? Because we're now going to go to the sort of margin classifier. Okay. So here's the sort of margin classifier. Yeah. So remember, this was the problem we started with, and oh my God, now we cannot separate it anymore. Right. So what do we do? And by the way, don't even think of, you know, going along and saying, hey, I just want to find maybe the linear separator with the smallest number of mistakes, because as we know, this is hard. So don't. And this is exactly another instance of, well, if you solve that problem by the letter, well, it's hopeless. But if you actually go and try and solve a slight modification of that problem, you can perfectly well solve it. So this was the idea, actually initially due to Bennett and Mangasarian for L1, and then, well, Cortes and Wapnick got hold of that paper, and then that became the soft margin classifier. So basically, Cortes and Wapnick did it for L2, Bennett and Mangasarian for L1. Yeah. So what's the idea? Well, we just take our inequality constraint, and well, if the problem's too hard, we just make it easier, right? So if w.x plus b less equal than minus 1 is too tight, well, we just make that constraint a little bit easier by, you know, adding some size to it, and we say those size can be greater or equal than 1. And likewise there. If this is too hard, we make it easier, but of course you have to pay for it. So you pay for it by, you know, simply adding, you know, by basically making this slack as small as possible. Okay. Now, here's a small intermezzo, namely, how do you actually solve convex programs? And the recitation will probably cover that in a bit more detail. Let's say I have some primal optimization problems. In a way, I walked you through this already before. And you want to solve it. Then you write out the Lagrange function. So the only thing you really need to be careful about is to get the signs right. Because basically, you want to set it up in such a way that you minimize it in the primal variables, and you maximize it in the dual ones. And the other way how to check it is basically by just making sure that that problem actually still remains convex in X. Right. So these are convex functions. Does everybody know that if you have the below set of a convex function, you get a convex set out of that? Does everybody know how that proof works? Okay, let me just draw a picture. It's a very high-tech proof. Convex function, below set. If we have any 2 points, well, the function value between those 2 points has to be below. That's the proof. Right? So that means any line between any 2 points is in the set, so therefore it's a convex set. So that's why I said it's a very high-tech proof. Now, it's the Lagrange function. Then you go and check for optimality in X. So you take the derivative, you set that to 0. So if you had an unconstrained problem, all those CIs would be gone. And this is exactly the first thing that you would do for optimality. You know, just look for where the derivative vanishes. And you go and solve for X. And if we had an unconstrained problem, then this is the end of it. If we have a constrained problem, we solve for X, plug it back into L, and now we have a, one would hope, smaller problem in a few alphas. And you keep those explicit constraints around if you still need them. That's it. So now we're going to play exactly that game, right? So this is what we have. And let's just look at our optimization problems. So the hard margin problem was one where we go and minimize, norm of w squared under the constraint that yi times w.xi plus b is greater or equal than 0. So large margin of separation. Now if we think that this is a little bit too hard, well, we give each of those observations a bit of slack. But of course you have to pay for that slack by just, adding up the slack into the objective, multiplying it by some constant c. The constant c is actually common, and I have sometimes received emails, at least in many years ago, from students who asked me, how should I set c? Right? That was the entire context in the email. It's just because, well, this is how Vapnik decided to call that constant, c, and so then, yeah. Yes. So the nice thing is that this optimization problem is actually always feasible. I mean, you can check that very easily, whereas the previous one, as you can clearly see, isn't always feasible, so you can't always linearly separate things. So if I set w and b equals 0 and set, psi I equals 1, I immediately get the solution of the problem. Another nice thing is it actually gives me an upper bound on the value of the objective function. This is good for debugging. So if you ever solve this thing and you end up with a value of the objective that's greater than, c times number of observations, you did something horribly wrong. Okay. Yeah. Actually, one thing of not having a feasible primal problem means that the dual problem actually becomes unbounded. So this is, and if you have a primal problem that's unbounded, the dual problem will become infeasible. So that you get this nice duality between primal and dual. So if you ever look into optimization, it's quite pretty. So here's the Lagrange function. Looks exactly like what we had before, with two exceptions. And conveniently they're color-coded, so if we add those slacks here, we have them also there. Should have color-coded that as well. And now one thing that we need to make sure is that those slack variables themselves do not become negative. Because what we want to avoid is that the problem essentially goes and says, okay, I have to pay some slack here. I can make up for it by essentially charging some observations that are very easy to classify some more. So that's why you have to impose that the psi i's are greater or equal than 0. And for that you basically need a second Lagrange multiplier. So you need eta. We'll make eta go away in short order. So now you have three sets of variables that you need to optimize over, namely w, b, and psi. And then you get a saddle point with alpha and eta. Okay. So the derivatives in w, b, and psi have to vanish, and here's what you get. The first two conditions are exactly what we already saw. Those exact same thing as for the hard margin. We just get one extra condition here. Namely, c minus alpha and minus eta I equals 0. Okay, now we go and plug everything back in. And there's a slight subtlety here, right? We know that the alpha i's have to be greater or equal than 0. We know that the eta i's are also greater or equal than 0. And what you'll see is that if you plug this condition here into the Lagrange function, you'll get all those linear terms in the etas and so on disappearing, so the etas show up nowhere at all. The net result is that you can actually get rid of the etas and the psi's, and it follows from that that the alpha i's have to be bounded between 0 and c. Well, the lower bound on 0 is quite easy because, well, just from the we know that from them being dual variables. The upper bound of c you can see as follows. You have alpha plus eta equals c. Right? And, well, let me just use pen and paper. So what you get is you get alpha I plus eta I equals c. we know that this is greater or equal than 0. We know that this guy here is greater or equal than 0. So therefore, we know that alpha I has to be always less equal than C. And that's about the only difference after you run through all the algebra that this change in the optimization problem gives you. So the change from the hard margin problem is you constrain the value of the alphas. Now, that's kind of nice because remember what I said, if you have an infeasible problem, the dual problem becomes unbounded. So whenever the dual problem would have wanted to become unbounded, well, we just put the hard upper bound on the dual variable. So therefore it's bounded. So therefore you can see it's always bounded, right? Easy. That also shows you that, you know, this problem is always feasible in primal. So the last thing that we need to do is we need to go through the KKT conditions, and then we'll have a slideshow. So the Karash-Kotak conditions, the first part is exactly as what we had before, except that now you can get points that actually sit on the wrong side of, you know, that margin. And those are exactly the ones for which alpha I equals C. Only those are allowed to push through the margin. So think of that as, you know, having two slabs which are now not made of steel but of some material where if you push hard enough you just stick through. That's it. So now let's look at some pictures. So, and for most of the pictures you will see that you don't see anything. So we'll just solve the soft margin optimization problem for different values of C. And lo and behold, you see nothing, right? Okay, now let's make the data a bit more noisy. Well, and you can see the margin gets a little bit smaller. The little faint green bits are the support vectors. Well, we have 3 of them in total. Right, you see nothing. Then make it more noisy. Not much happens. Make it even noisier. Oops, now something interesting happened, right? So what you can see is that there are now a whole bunch of points inside that margin, or possibly even on the wrong side. But first of all the blue stars, all the blue dots, none of them is beyond the margin, you know, has a green circle around it, so none of them is support vector if it's on the correct side. Likewise here. But, you know, you can have some points inside here and on the wrong side. And now as we crank up C, well, basically what it'll try to do, actually, does somebody have an idea of what will happen if we increase C? We basically allow each point to push a little bit harder. What do you think will happen to the margin? Get smaller. Who votes for smaller? Who votes for larger? And the rest is asleep. Okay, good. Smaller. Yes. So that's exactly what happens. But not that much, and a little bit, and a little bit, and a little bit. So that essentially pushes observations out from there. But you can see it's actually not super sensitive to the specific value. And here's the dual problem. And this is what we'll conclude with today. So you basically solve that problem. And if the problem is small enough, like thousands of variables, well, you can just use whatever off-the-shelf solver. Even MATLAB will do, but be careful with MATLAB solvers. I don't know whether they are good now, but at one point they actually will give you wrong answers. You can just use any off-the-shelf solver. Most of them will do. For larger ones, you pretty much have to write your own code, or at least download somebody's optimized code for that. So that concludes it for today. If you have any questions, let me know. Cameraman, please push the stop button.